equation is the definition of the derivative. It may look scary, but all it is m, which is slope y2 minus y1 over x2 minus x1. At y2 being f of x plus h, y1 being f of x. X cancels out to become h because all you're doing is x2 is x plus h, which is h is just a tiny time. X plus h is a time plus a tiny bit more. That's all that x plus h is. Minus x, which is just x1, just leaves h. Why do we have a tiny time? Well, if we're looking for the instantaneous speed, a speed at one point in time, if we cut out the time to find that one point, we pause time, we're only going to be left with no distance because the car is no longer moving, or whatever object is no longer moving. So we need a tiny time h. If we're given the position function, which equals t squared, and we want to find the velocity at time 1 second, well, we can use the definition of the derivative to find the velocity at 1 second. All it's going to be is the limit of h approaches 0, the tiny time, where t plus h is the x plus h squared, because it's the function, minus t squared, the y1, over h. So we can simplify this by using the quadratic. T squared plus 2th minus t squared over plus h squared over h. So this t squared minus t squared cancels out, just subtraction, leaving the limit as h approaches 0 of 2th plus h squared over h. Now we can simplify this even more by taking out, factoring h, 2t plus h over h. The h's cancel out by division, leaving the limit as h approaches 0 of 2t plus h. Well, if h approaches 0, we can plug in 0 for h because we know it's just very close to 0, leaving 2t plus 0. Why couldn't we plug in the h before as 0 all the way back here, save us all that work? Well, anything divided by 0 is undefined, so we had to wait until we no longer had a fraction with h on the bottom. Now we know the velocity of t equals t squared, because that's the derivative of the position equation. All we have to do now to find the velocity at 1 second is put in 1 second for t, which leaves 2 meters per second.